to this point, if you're in my class watching this, to this point we have seen explicit relationships between acceleration vectors, velocity vectors, displacement vectors. We have also seen explicit relationships between force vectors and acceleration vectors, right? We have kinematics to give us these, and we have Newton's second law to give us these. But if you've been paying attention, hopefully you have, you might have noticed that the kinematic equations, right, are only valid for constant acceleration. Newton's second law, of course, is valid for all cases where a force is applied to an object. So there are lots of scenarios where I cannot get from a force to things like a velocity or displacement. If the acceleration is constant, I can start out with a force, then determine the acceleration, then go to kinematics. But if the acceleration is not constant, that bridges out and I can't get here. So I don't have an explicit relationship between forces and displacements or forces and velocities. I mean, I don't have an explicit relationship yet for anything. I just have a secondary relationship. But if I don't have a constant acceleration, I don't even have that. So what we're going to do now is attempt to develop a set of tools that will give us an explicit relationship between forces that act on objects and things like their accelerations, forces that act on objects and things like their displacements and velocities without going through the acceleration. We are in the section of the class in the textbook where we are going to talk about work and energy. So these words are sort of famously hard to pin down, at least non-mathematically. Which mathematical definitions are just fine. We're gonna need them, right? But remember that mathematics describes the universe. Mathematics doesn't govern the universe; it describes it. And so, if we're gonna be describing something mathematically, it seems like we should be able to talk about what it is in just everyday language. But it turns out that this is really hard to do for work and energy. Your book if you're in my class, your book defines work as energy being transferred to an object, and I'm just fine with that definition, but that then doesn't tell you what energy is. It turns out, I think the best we can do here, at least at this point, is to define these terms intuitively. We all have a good idea of what energy is. We know that it takes energy for our bodies to run. We know we get that energy from food. We know it takes energy for our cars to run, and we know we get that energy if we have internal combustion engines from gasoline. If we have electric vehicles, we get it from a battery. So we know this. And then if I say that work is the process of energy being transferred to an object, that means that when you, in some sense, when you're putting gasoline in your car, you're doing some work on it. Now, we're going to define work a little bit more rigorously than that, but you should have that in the back of your mind as a good way to start thinking about these things. Energy is what we need to function, right? And I realize that that's really non-specific, but we all have an intuitive understanding of that, and I think that's where we're going to start. But we are now going to develop the mathematical definition of work. We're not develop it in the sense of derive it, but we're going to talk about it. So let me give you that mathematical definition of work. We've got the symbol for it is W is equal to the integral from point A to point B of F vector dot dr vector. So let's talk, this is the definition. I should give you 3 lines. Normally when I do mathematical definitions like this, I just put it up there and then we talk about what it means. So first let's figure out units here. Units of work are going to be, well, whatever the units are here. So what are the units of force? Well, we've got a Newton. And this is a displacement. Let's talk about this first. dr is a displacement variable. It's my general placeholder for a displacement variable. To this point in the class, I've probably been using x's, and I would say things like, you know, if you see an x, it might as well be a y, it might as well be a z, but I don't want to write down all these equations 3 different times each, so I'm just going to give you an x and tell you that make it a y if you need it to be. This is our new general displacement. This, in some situations, will turn into a dx. In some situations, it will turn into a dy. Sometimes it'll be a lot more complicated than that. But when you see this, this is a displacement vector. So units of displacement are meters. A Newton times a meter are the units of work. But of course, nobody says that. Physicists, being inherently lazy, wrap up units and name them after somebody, right? That's what we did with newtons. Newton is a kilogram times a meter per second squared, which means that you could talk about work as a kilogram times a meter squared per second squared. But nobody wants to write that down. So we wrap all that up and we name it after James Prescott Joule. That's Joule, symbolized with just a J. So units of work turn out to be joules. All right, so that's the units of work. Now, I've already talked about the displacement. Let's talk about the integral first. When you see an integral, that tells you something really specific. And you're like, well, yeah, it tells me to, pull out my integral tables or, go through my Cal 2 processes. And while that's true, that doesn't tell you what it means. But we've talked about, in this class, if you're in my class, we've talked about this. But just as a refresher, or maybe if you've never heard this before, the integral symbol itself is an S. What that means is that you are going to do a summation. An integral is addition. Only you're not adding discrete quantities. This one plus this one plus this one plus this one. You have a continuous quantity, and it doesn't make any sense really to say, well, just add up, with a simple plus sign, this amount plus this amount plus this amount. If you have a continuous quantity or a continuous distribution of something. So to do that, we have to integrate. But integration is just addition. It is summation. I'm adding together some things. So the idea here is I'm doing little bitty differential elements of work, and then I add all that together to get total work. That's what an integral is. The points A to B, the definite integral, tells you that this integral is performed in space. Turns out work and energy are not vectors. They don't have a spatial direction. But if you're doing work on an object, you are moving it from in space from one point to another space. So while work and energy are not vectors, the work you're doing on an object turns out to need spatial dimensions. And so I'm moving this thing from point A to point B, and I get the work done from there. Now, force, I think that's pretty obvious, right? But just so we know what we're talking about, this could be any force that we've talked about in this class so far. We've talked about contact forces like tension and friction and applied forces. We've talked about gravitational forces, at least somewhat. We haven't given the full treatment of gravity yet, but it's coming. This could be any force that we look at. We're going to look at spring forces a little bit later. It turns out in physics too, you're going to meet a force that doesn't work here. Doesn't give you any work. It's the magnetic force. But for now, everything we have here, everything we've developed in this class so far, works just fine to be put in here to see how much work that's done. All right, so we have a force, we have a displacement. Now, please notice that if you have a force but no displacement, work is not done. If you have a displacement but no force, work is not done. The total force turns out to be 0. You got to be very, very, very careful with that. Just because you have a force does not mean there's work. Just because you have a displacement does not mean that there's work. You have to have both of them. Let's talk about how we're multiplying these things together. This is the dot product. If you don't know what a dot product is, and if you haven't been through Cal 3, there's a good chance that you don't. I have a separate set of videos. I think actually it's just one video on this playlist of the dot product. So stop this video and go watch that before we continue. We'll wait. All right, welcome back. So what is the dot product? Hopefully you've seen it on the videos. I'm just going to give you a quick rundown here. The dot product of any two vectors, vector A and vector B, is defined as magnitude of A times the magnitude of B times the cosine of the angle between them. So first of all, I would say magnitude, just a number, right? This is not a vector. The dot product gives you a scalar. Sometimes it's called the scalar product. I said a while ago, work and energy aren't vectors, so check, that works. We'll see later in the semester there is a way to multiply vectors called the cross product, which does give you a vector. But for now, we're using the dot product. The cosine theta here serves as an interesting function. Just as a reminder, That's the angle between vector A and vector B. What this tells you is that there are certain situations in which in any situation, the actual dot product varies due to factors other than how big the vectors are. How they're oriented plays a big role. Let me give you an example from, if you're in my class, one of the homework problems you've done. All right, you had a box on a ramp, and you were trying to push it up the ramp, and to do that, you were applying a horizontal force that looked like that. And the box moves up the ramp. So there is my delta R, right? dr. In this case, I'm going to let that be some sort of, actual not differential element, some sort of change in R. Of course, we know from calculus, if we let this delta R shrink down to infinitesimal proportions, we get a dr out of it. In this case, just leave it as a delta R. But I undergo this displacement. But look at the orientation of the force to the displacement. They're not collinear. In point of fact, to figure out how effective I'm being, and instinctively you probably know that this is not the most effective way to do this. If you've ever pushed something up a ramp, you know that you shouldn't push horizontally. Let's break this force up into components. Assuming that my coordinate system is rotated to match my plane, I have this component and I have this component. We'll call this Fy. Why not? This is my force. Since I've already called this the R direction, let's not call it Fx, let's call it Fr. So what's happening here? Well, what is the angle between Fr and delta R? I see an angle of 0 degrees. Well, what is the cosine of 0? 1. So look at this. Fr does work on the box because the box moves through a displacement along the same direction. We say collinear as Fr. Fy, though, has an angle of 90 degrees with respect to delta R. Right? The angle between this vector and this vector is 90 degrees. What's the cosine of 90 degrees? Nothing. It's 0. So I shouldn't say nothing. It's 0. 0 something. So Fy actually doesn't do any work on the box. Fr does work. So what can we take from this? Well, we can take from this that not only do I need a force and a displacement, I need some part of that force in the same direction as the displacement. So there's 3 things to consider. I said a while ago, if I don't have a force, I don't have work. And if I don't have displacement, I don't have work. Now I can say, if I have a force and a displacement, but those 2 vectors are orthogonal or perpendicular to each other, I still have no work done. That means that force is not doing any work on the object. Okay? This means that different kind of forces produce different amounts of work. If this is a friction force, think of what that looks like. Let's go to a different sheet. Friction always opposes the motion. So let's imagine that you're pushing something along a path that looks like that. I'm looking at it from above. And so we're just going to look at the work done on the object by friction. So let's say that we're going to look at several different points, right here, and right here. Let me get a different color here. At this point, dr, there's my dr, my displacement direction, basically. And here, dr has shifted, right? I'm turning. I'm going around a curved path, and so my dr is constantly turning. But if friction always opposes the motion, that means here, if my motion is along this line, then friction is along that line, right? We'll say this is kinetic friction because I'm moving. Here, if my motion is along this line, that means friction is along that line. My pen is running out of ink. Here, same thing. And so as I turn this thing, I always get this frictional force that opposes it. That's just the nature of friction. And so you can see pretty quickly that how much work I do on this, or not me, how much work friction does on this object depends on how long a path it is. Right? If I'm always getting the full force of friction in my work calculation, then I can find different paths that are going to give me different amounts of work, right? If I take the straight path, so I should say here's point A and here's point B to match this up with what we've seen in our integral. This is a path integral from point A to point B. So if I go along this curved path, I get a certain amount of friction. But if I go along this path, that's supposed to be straight, I'm going to get friction, but you can probably see that it's not going to be as much. I should say it like this. I'm not going to have to add up as many elements of work as I did along this curved path if I go straight. Why? Because the path is shorter. We know this, right? If you need to push a couch from here to here across your living room, no one ever goes, well, let's just take this circuitous route. Let's take the scenic route to push a heavy couch across my living room. Doesn't make any sense. You want to go from point A to point B without passing through all these other points. Now you can say that that's because it takes less work to do that. I'm not adding up as much of these dr.f's, and these should all be vectors, sorry. If I were to take this path, I'm not sure why I would. Maybe, whoever is telling you where to put the couch doesn't actually know where they want it. And so they're like, well, let's try it over here, try it over here, try it over here. It happens. There's a lot of work being done along this path. So a little bit of work, more work, a lot of work because the path is longer. That's what happens with something like the friction force. But something really interesting happens if I look at a different kind of force. I should point out, this happens because the friction force turns along with your displacement, right? It always is matching your displacement. Exactly. But if I have a force that doesn't do that, I'm going to get a really interesting result. So let's say that I'm pushing an object up a ramp, like I had a while ago. And let's say that what I'm really interested in is not the work done by friction or even the work done by the applied force. What I'm really interested in is the work done by gravity. Okay, well, gravity always looks like this. And the displacement of this thing, if I'm pushing it up the ramp, looks like this. So gravity is not in the same direction as the displacement. There is a component of gravity that's in the same direction of the displacement. We've seen that when we did free body diagrams on inclined plane problems. All right, what I get out of this is mg sine theta. Right, remember that? Theta is right there. So this component of gravity does work here, but the full force of gravity does not. I should point out, because these are opposite, what's the angle between them? 180 degrees. And what is the cosine of 180 degrees? It's not 1, it's -1. We say in this case, we would be doing negative work. That's okay. Nothing wrong with negative work. But in this case, the component of gravity is doing work here. This gets even more interesting when I have something moving, let's say, in a circle. So let's say I have something moving like this. And so I'm going to look at the point right here, and the point right here, and the point right here, and the point right here. So as this thing is moving, let me draw in the DRs. There's one DR. There's another DR. There's another DR. There's another DR. So this thing is moving in a circle. Well, let's look at gravity at every one of those places. Right? So, we can look at here. If there is a point here, and I tried to draw it, where those are orthogonal. How much work is gravity doing at this point? Well, the answer is none, because the angle between them is 90 degrees and the cosine of 90 is 0. Gravity is doing a significant amount of work here because these are almost lined up. But we're back here to no work, and then here a significant amount of work because these are also lined up. And of course, there are intermediate cases. As I move around, the amount of gravity is in the same direction as the displacement is constantly changing, and so the amount of work I do is constantly changing. But gravity is an interesting one because gravity is what we say is a conservative force. Gravity is a conservative force. Now let's talk about what in the world that means. Well, let me ask you this. Let me go back to this situation where I'm pushing the mass up the ramp. Let's say that I push the mass up the ramp and in that case gravity is doing a certain amount of work. Now, of course, if I'm pushing it, I'm also doing some work, but we're not considering that yet. We're just considering gravity. How much work is gravity doing on this thing? So I push the box up the ramp, gravity does a certain amount of work, and then I let the box come back down the ramp to its initial point. Gravity also does a certain amount of work there, this component of gravity. But what's the total displacement if I go up and I come back down? My total displacement is actually 0. That's really interesting, because if I go back over here and I look at this and I say, okay, well, the total amount of work done then has got to be 0 because my total displacement was 0. That is to say, once I integrate this, I find that my displacement turns out to be 0, and I get 0 from the work done. Now, let's think about that. For gravity, maybe that makes some sense. If we're talking about friction, that does not make sense, because friction always opposes the motion. If I push the box up, friction is going backwards. And then if I let the box come back down, friction is now going up the ramp. Gravity hasn't changed, but friction changes direction based upon the motion. So to put it mathematically, if gravity's down the ramp, always down the ramp, if I push it up, gravity's down the ramp, I get negative work. If I then let this thing come back down the ramp, the displacement is down the ramp, and gravity is down the ramp, I get positive work. So I get negative work going up, positive work coming down. Guess what they add together to give me? 0. That's not the case for friction. Friction gives me some negative work going up, and then because it flips around as I come back down, it gives me more negative work, and so you cannot add a negative number to a negative number and get 0. So you've got to be a little bit careful when thinking about this. Just because your displacement is 0 does not necessarily mean that there was no work done. That depends on what kind of force this is. If this is a friction force, you've definitely done work, right? You've got to move it back around. Think about taking a couch across your living room. Let's say that whoever you're living with says, I want it over here, and you move it over here, and they say, oh, I want it back over here, and it goes over here. You know, I liked it better where it was originally. Put it back. Have you done some work? Absolutely you have. So friction does work no matter what path you take, but it turns out that gravity is not that way. So let me rewrite the formula for work and make one small change. Work is equal to the integral a to b f dot dr. If, that's 2 F's, that's math speak for if and only if. That means necessary and sufficient condition. If and only if this is the case. From point A to point A. And the implication here, I'm going to rewrite this more mathematically in just a second, but the idea is you're actually moving along some path, but you get back to where you started. You start out at point A, and you start out at and you end up at point A. If that's the case, and if you have work is equal to 0 for that, then we say that F is conservative. That is, the work done does not depend upon the path. Friction is the prime example of a non-conservative force. Gravity is the prime example of a conservative force. It's because gravity is constant in direction. The more mathematical way to write this is this. The circle means a closed path. It means that point B is point A. You get back to where you started. The closed integral of f dot dr equals 0 if and only if f is conservative. This actually functions as the definition of a conservative force. So this is very, very, very important. Gravity is conservative. The path does not matter. uh, gravity is conservative. The actual path you take does not matter for the amount of work done. All that matters is the beginning and the ending points. If it turns out to be a closed path, you get 0 work. If it's not a closed path, right, you get some work, but the work does not depend upon the path you took. If you're dealing with friction, it absolutely depends upon the path you take, because friction is not conservative, but gravity is conservative. All right, that's something to think about. I don't expect you to really just grasp that after this short conversation. But that's something to think about, read your book about, and we're going to use that to make some problems easier to solve.